but this one slightly differently, talking about some recent model results that we've been looking at in terms of the neutral, atomic, and ionized Phobos torus. And I particularly want to sort of touch on what are the implications for spacecraft observations. Most, or if not all, of the papers or presentations to date have all been theoretical or modeling. But I think at the end of the day, we'd really like to be able to measure that. And being able to measure that requires understanding of what perhaps is the best way to go about sending an instrument to Phobos and Deimos. So this obviously is now the third in a row that you've heard about dust and gas torus at Phobos. In fact, this idea is not new. It's been around since the 70s. I list a handful of observations that have maybe suggested these odd Phobos events. Are they indicative of a sort of Phobos, either neutral or gas torus that's concentric with the orbit of Phobos? There's theory, another one concentric with the orbit of Deimos. But again, none of this has ever been measured. So based on a lot of the work that I personally had done recently with the Lottie mission, a lot of those same processes should apply to Phobos and Deimos. So I started looking at this. And immediately two main questions came to mind. Can we really understand what the neutral distribution of species sputtered from Phobos is? And those neutrals, once they're in orbit around Mars, will eventually be ionized. And can we understand what the distribution of this ionized material is spread out throughout the Martian magnetosphere? And these, one or two of these ways, could potentially be mechanisms to observe this. So how do we generate a neutral torus from Phobos? There's actually a number of mechanisms, but I'll touch on three right here. The first is charged particle sputtering. We've heard about this just briefly from Micah. So you have solar wind and planetary ions that come in, they impact the surface. They tend to have yields that span anywhere from about 10 to the minus 3. Planetary heavier ions, such as oxygen or carbon dioxide, can actually sputter at a yield of about unity. So these can be very efficient sputtering mechanisms. You can also have micrometeorites that impact the surface. In addition to ejecting solid dust off, they will actually vaporize part of the surface, so you can get direct injection of neutrals from micrometeorite bombardment. And finally, a third mechanism is actually photon-stimulated desorption or photon sputtering. The quantum mechanics of this mean that it's highly species-specific, and in fact, sodium and actually potassium as well is well known at the moon from this effect. For this talk here, I'm going to focus just on charged particle sputtering. If you work through some sort of back-of-the-envelope calculations about what the relative rates of these might be, charged particle sputtering should be the dominant one by at least an order of magnitude or not more, so I'll really focus on this in the talk. So if we're going to understand charged particle sputtering at Mars, we need to understand the plasma environment that Phobos is sitting in. What I'm showing here is a cartoon from Andy Nagy et al. 2004, and the cartoon is sort of showing in gray the general structure of the Martian magnetosphere. Upstream and to the side you have the solar wind, it's undisturbed, but as it encountered Mars, it forms a bow shock, a magnetosheath. This is very hot, turbulent solar wind plasma that's being diverted around Mars. And then you also have downstream from Mars the Martian magnetotail. This is much more tenuous. There's not a lot of solar wind plasma in the tail. However, Mars itself is actually a very prodigious source of planetary ions. The atmosphere of Mars is directly exposed to the solar wind. It forms this very narrow ionospheric layer on the day side. And in fact, a lot of the atmosphere of Mars can be ionized and stripped away. This is in fact one of the major observational goals of the MAVEN mission is to measure this flux of planetary ions. The cartoon that you're seeing here is representative of the sort of general structure of where these fluxes exist. You can see it's highly asymmetric, and that's mostly based on electric fields in the solar wind. The electric fields like to point a specific direction. You're accelerating a lot of pickup ions. They call this the plume of pickup ions coming off one side. But you can also see there's a healthy dose of oxygen and carbon dioxide molecule, or ions, excuse me, that are kind of leaking down the Martian magnetotail. And you can envision the orbit of Phobos. It's passing both in the undisturbed solar wind up here, but once every orbit, it's kind of wandering through these heavy planetary ions. And these heavy planetary ions, again, are important because a single O+ ion slamming into the surface can eject 100 times as many neutrals as a single proton. Impacting the surface of Phobos. So for every one of these, you get about one neutral out, but about every one proton, you only get 1 in 100 neutrals out. So these are actually both important to take into account. So to quantify that, a couple years ago, myself and Shannon Curry, another postdoc at Berkeley, put some models together that looked at both the flux of solar wind, protons, and these planetary ions from Mars. We walked through the calculations of how much neutral material that would sputter from Phobos. And the plot that I show here is a single orbit of Phobos about Mars in local time. So this is midnight in the Martian magnetotail, and 12 noon is out in front of Mars in the solar wind. The red dashed line shows you about how many neutrals you expect to be ejected from solar wind fluxes. You can see it drops out in the magnetotail where the solar wind is blocked. But it's immediately replaced by this gray bar, which is actually planetary ions. These are oxygen, carbon dioxide that are coming from Mars itself and impacting Phobos. And you can see it at certain times in Phobos' orbit. These fluxes from planetary ions are actually more efficient at sputtering neutrals. So in reality, you should actually sum the two of these together to get the total rate. Walking through that, you can get a total rate of about 10 to the 19 per second. To put this in context, this is actually a very low number. When the Phobos mission was first launched and they kind of observed these Phobos events, they walked backwards and said, well, what kind of production rate would we need from Phobos to generate these events? And they came up with the numbers about 10 to the 23 per second. So these calculations are much, much smaller. So with respect to estimates that we were getting from earlier missions, this is a very low number, and that'll translate throughout the entire simulation. So in order to actually look at how these neutral distribution is, we used a neutral Monte Carlo. It basically just follows neutrals as they're ejected from Phobos throughout the Martian gravity well. They're lost from a couple of different processes, collisions with Mars, escape, or ionization. We took sort of a rough estimate for the surface composition. These are obviously somewhat uncertain, but it's a dominantly silicate surface, so you have a lot of oxygen, a lot of silicon, and a handful of other minor species. So here's what the neutral distribution looks like from Phobos. You see Mars in the center. Phobos in this snapshot is located off at dusk. This is looking in the ecliptic plane, while this is a cut in the meridional plane. And you can see it's not exactly a torus so much as sort of a series of arcs. There's this big plume right here that's coming directly from Phobos. Those are neutrals directly sputtered from the surface that have velocities higher than Mars' escape velocity, so they're just essentially spraying out into interplanetary space. But there's some fraction of these neutrals that have velocities below escape velocity, and due to some differing orbital mechanics as they orbit around Mars, they're most concentrated where Phobos is, and they're sort of depleted and kind of smeared out closer to Mars on the far side. When you take a cut through it, you can see actually it extends several Martian radii above and below the orbital plane of Phobos. But this is essentially what we would expect these neutral distribution to look like. And the example I is for oxygen, but we've done this for all the species. We have oxygen, sodium, magnesium, aluminum, silicon, and iron. They mostly have the same general shape. You can note a couple of differences. Aluminum actually only has this plume. It's a sort of a quirk of quantum mechanics. Aluminum has a very high photoionization rate, so actually the neutrals don't even get a chance to orbit even a fraction of a way around Phobos before they're ionized and lost to the solar wind. But in generally, it's the same shape overall. Now the total densities, this is where it gets a little bit challenging. When you actually put in real numbers to what these fluxes should be, you end up with neutral densities that are 10 to the -3 per cc. That's incredibly low. It's much lower than I think any in situ neutral mass spectrometer can actually measure, akin to something like the NMS instrument on LADI. Would never be able to measure densities this low. So this is actually an incredibly challenging, if not impossible, mission to make measurement to make with direct neutral mass spectrometry. But we know that these neutrals, as they're orbiting around Mars, are going to be ionized. And once they're ionized, they become pickup ions, and they respond to background electromagnetic fields. Pickup ions are actually a very handy way of measuring exospheric composition at lots of bodies. We've had a lot of success with this at the moon from the Artemis mission. And the reason goes that it's much easier to detect a single ion in the electrostatic optics than it is to measure sort of the neutral density in the background. You can get much finer sensitivity when measuring ions. So to keep exploring this, we put together a second model that essentially takes the neutral distributions that we generated in the first model, it ionizes them, it runs them through a background electromagnetic field model that we have for Mars' magnetosphere, and it goes through and it calculates what this distribution of fluxes should be. To do this, we first had to look at what the ionization rates are. There's three important mechanisms to ionize a neutral. You can photoionize it, you can electron impact ionize it, where an ambient electron just smashes into the neutral and ionizes it, or you can have charge exchange with solar wind protons. Each of these processes varies not only by species. A lot of the quantum mechanics comes into being important for how efficient these processes are, but it also varies in different regions in the Mars magnetosphere. You have different electron densities, or different electron temperatures, or solar wind. The plot that you're seeing here is by species. We have oxygen, magnesium, silicon, sodium, aluminum, and iron, and the blue colors are essentially telling you the total ionization rate. So I mentioned earlier, for example, aluminum has the highest photoionization rate, so anytime the aluminum neutrals are in sunlight, they're very rapidly ionized. These other structures that you can see in the other ones, this sort of bow-shaped structure is the Martian magnetosheath. The electron temperatures are hotter, so electron impact ionization is more efficient there. But using these compiled ionization rates, we can actually put the neutral model into these ionization rates and generate pickup ions and look at their fluxes. That model produces a lot of results, but I'll go ahead and highlight a couple here. This is for aluminum ions, silicon ions, and iron ions. And what you're looking at is in the ecliptic plane. Mars is in the center, and the dashed line is Phobos' orbit. Phobos, in these simulations, I put at noon. And you can see the color denotes the amount of pickup ion flux. Aluminum, again, since it only has this small neutral cloud, really only produces a single little beam of pickup ions, but silicon and iron, which have a much broader neutral distribution, have this much broader pickup ion distribution as a result. The flux is in the tens to maybe 50. Once you add it all up, it's about 10 to the 2 per centimeter squared per second. This is difficult, but not entirely unrealistic for a particle spectrometer to measure, something that's been on MAVEN in orbit for a little more over than a year and a half at Mars now. So these kinds of simulations tell us that there's still a little bit of hope to be able to measure some of these ions. So in conclusion, we believe that based on all of our previous knowledge at bodies such as the Moon, Phobos should produce a neutral torus. However, this neutral torus is very tenuous. It's highly unlikely to be able to measure it with direct in situ neutral mass spectrometry. But pickup ions may be the way to solve this measurement because plasma instrumentation is a lot more sensitive. And in fact, one of the big future works to do in this is to look for extreme events. We have solar wind disturbances that might amp up the neutral torus temporarily, and really to dig through the MAVEN particle data. I don't know that anybody's quite yet got through it, but there's plenty of data now to maybe either look for case studies if the solar wind and Phobos orientation are just right, that MAVEN should be in the right spot, or to look at a little bit more of a statistical analysis, maybe the way forward in this. The details, probably more details than you'd ever want about this model, are in a recent paper in JGR Planets. And with that, I'll conclude. So, thank you.
So I haven't read the paper, I should, but have you looked at the distribution of ejection velocities of the neutrals?
Yes. I don't have a slide. That's a good question. But what I can point you to is something, something like this plot. And you can actually see that the higher velocity neutrals are those ones creating this sort of sprayed off sort of plume directly in interplanetary space. And the slower distributed ones sort of end up forming this sort of narrow ring. So.
This was really good. Can you comment on what would be happening with Deimos?
So, Deimos should essentially have all the same basic underlying physics. It's going to get sputtered, it's going to lose neutrals, they'll be ionized, et cetera, et cetera. But you have two things working against you. Deimos's physical cross-section is much smaller, so you're going to generate fewer neutrals overall. And since its orbit is farther away from Mars, you're taking that smaller number of neutrals and you're distributing it about a greater space. I believe, I didn't actually run the neutral model because when I did the back of the envelope calculation, it's 1 or 2 orders of magnitude even less dense than the Phobos torus. So if you really want a challenge, go look for the Deimos torus.
So just a quick question. Do you have a ballpark of what is the amount of flux material that's removed through this process compared like to the dust being deposited by Deimos? I mean, we're talking, do you have any idea in terms of kilograms per day, year, month?
I don't think I can do that conversion in my head. It's as simple, actually, as taking 10 to the 19 per second and dividing by the surface area of Phobos. My gut would tell me it's probably not quite as efficient as the micrometeorite redeposition. So.
Okay, thanks.
Okay, so thank you. Speaker?